Hello, Ishwan, are you there?
Oh, yes, I'm here.
Thank you. Thank you for your support.
Oh, it's okay.
Okay, okay, good. So speaker is not yet here. As soon as, speaker zoom in, then please make her a co-host.
Okay.
Maybe for a while I can, is recording in progress. Can you make me co-host?
Oh, okay.
Yeah. Now I can pause.
Okay, so I get started. So today I'm going to talk about coarse-grained reconfigurable array or CGRA. Now, most of you might not be familiar with this particular term or the architecture. So what I'm going to do is that we're going to go through a little bit of a motivation behind this particular class of architectures, where they stand in the entire landscape of very different architectures. And then we are going to delve into the details of the CGRA architecture as well as the compiler for CGRA. And finally, we are going to focus on some of the tools that we have in our lab that you could use to explore this architecture in more detail. So today I'm joined by two of my PhD students, Thilini and Zawing, as well as postdoc researcher, Dr. Dhananjaya. And they are going to take part in part of this presentation. So I'm Tulika. I'm from the School of Computing at National University of Singapore. I'm a professor at NUS. So this is in Embedded Systems Week, and one of the first embedded systems that you can think of where we have ICs being used in embedded systems is I could find this hearing aid device that was produced in 1964. And one of the big deal about this particular device was that this IC had 22 components that were put together in order to create a custom integrated circuit which could be used in the hearing aid. So this is a big deal, and this was designed back in 1964, and this is sort of, you can think of one of the first embedded systems that was designed using IC. But the point is that these systems were very specialized designs, so they were designed for one particular application. So since they are designed for one particular application, they can offer you very good performance, they can offer you very good power efficiency, and they're very cost effective because they can only execute one particular application. As the integrated circuits increased in complexity, of course, we had design automation tools that were introduced to reduce the development time. And we had a number of specialized circuits, which we call the application-specific integrated circuits, or ASICs, that were dealing with this kind of custom IC design. All of that kind of changed in 1971 when Intel introduced its first microprocessor called Intel 4004. This was a general purpose programmable processor, which is what we are familiar with today. And it introduced the von Neumann architecture with the stored instruction concept. So that means you have the instructions stored in the memory, and you fetch those instructions, you execute those instructions, and you write the data into the memory. So this is the internal architecture of the Intel 4004. And if any of you have taken a course in computer organization or architecture, you would be very familiar that this is very similar to that 5-stage pipeline. Now notice that this particular architecture only had 2,300 transistors, and it was designed at 10 micrometer technology. But the greatest thing about this was that this was a generalized architecture that could support many different algorithms. So this was a universal hardware that can support many different algorithms and applications rather than being a specialized hardware. Indeed, this particular chip was used in printing calculators, cash registers, ATM, etc., etc. So the big point about von Neumann model of computation is that it's a generalized architecture. So there is a well-defined interface between the hardware and the software, and that you can have through the instruction set architecture, right? So that's the great thing about it. So the software developer can just develop for the instruction set architecture, whereas for the hardware designers, they can make all the optimizations under the hood, and those do not become visible to any of do not become visible to the software, or the software programmers do not need to worry about it. So this kind of systems offer high programmability, so you can support all kinds of applications, right? And between 1980 to 2005, there has been unprecedented growth of microprocessor due to Moore's law, Dennard scaling, and of course, microarchitectural innovations. So Moore's law, all of you are kind of familiar with Moore's law. So the transistor density basically on an integrated circuit doubles every 2 years. So if I have 100 transistors here, then in 2 years, I'm going to have sort of 200 transistors, right? Now, there are certain factors that sort of changes because of this. So first of all, since you are shrinking the transistors, so you are increasing the number of transistors by a large amount. And so as you can see that the transistor size is decreasing and it has kind of reached, a very, very, very small size. Now, as you decrease the size of the transistor, it can also actually switch faster, right? So you can actually get higher frequency. So that's the main benefit of Moore's law, that you are being able to pack more functionality and then you are increasing the frequency of the transistor. Now, one of the reasons that Moore's law was successful because it was complemented with Dennard scaling. And this, some of you might not be familiar with. So the point is that as the transistors get smaller and smaller, so you have more transistors on the same chip area, right? So in the same chip area, you have more transistors, which actually can mean that you are generating more power. But what was happening is that both the current and the voltage was also scaling. And so that means that the power dissipation was scaling as well. So even though you are putting more transistors in the same area, the power density remained the same. And this was the big reason why we could kind of have the scaling that was happening. So in conjunction with Moore's law and Dennard scaling, there has been also significant microarchitectural innovations. So basically, you compile your code, it generates a sequence of assembly instructions, which also finally gets converted into machine code. And then the processor basically takes this sequential stream of instructions and tries to find out which instructions can it execute in parallel, which instructions are dependent on each other, and so on and so forth, right? So all of these things are actually happening inside the hardware. So here is, for example, I have the AMD Zen 4 microarchitecture. As you can see over here, you don't need to look at the details, but it uses a lot of things. It has a really large cache. You can see the L1 cache here, L2 cache, L3 cache. We have branch prediction, value prediction. We also have out-of-order execution. So for example, you can see the reorder buffer here that has 320 entries. So it can bring in all the instructions, it can find out all the dependencies, and it can execute those instructions. So that has very high energy overhead. Moreover, because you are trying to do it in hardware, there is limited parallelism that you can exploit. So that means that these systems, first of all, cannot be very energy efficient, and second, they can only explore limited parallelism. So we kind of reached the end of Moore's. We kind of reached the end of Dennard scaling back in 2005, and then we also hit all these instruction level parallelism wall, energy wall, memory wall, etc., etc. So it became almost impossible to increase the performance through instruction level parallelism as we were doing before. And so we switched to multi-core and many-core architecture. So here is one example from AMD. This is an AMD server with 12 CPU die, 96 cores. This is a huge architecture. And if you look at this, right, so we talked about 2,300 transistors in the first Intel microprocessor. What you are looking at here is 6.57 billion transistors per die and 360 watt of TDP. So this is kind of a really, really large system. Unfortunately, even with 96 cores, it's not possible for you to exploit all the parallelism. Moreover, there is this other issue with Amdahl's law. So what Amdahl's law essentially says is that if you have a program and you can actually parallelize, let's say 99% of the program, but you still have 1% that you could not parallelize because it's sequential, maybe you are just reading the data. And that's true for most programs, right? For most programs, we would be lucky if we can parallelize 90% of the code. So if I cannot parallelize, let's say 1% of the code, then no matter what I do, the speed up that I can get is 1 divided by the sequential portion. So that means I can get a speed up of up to 100, no matter how many processors I use, because it's bottlenecked by that sequential fragment. So because of all these things, this is the evolution of the computer architecture landscape. This is a paper from Norman UP in 2018 in Communication of the ACM. And what you can see here is very, very interesting, right? So, what we talked about. So end of daylight scaling, you go into multi-core, your performance is increasing by about 23% per year. You get hit by Amdahl's law, so it starts increasing about 12% per year. So you get bottlenecked by the sequential portion. And then even Moore's law is coming to an end. So what you are kind of now reaching is end of the line, which is performance improvement of 3% per year. So of course we don't stop, our innovations simply because of these challenges. So we moved into this era of domain-specific hardware accelerators, which are everywhere today, right? So instead of general-purpose processors, now we have these very, very specialized architectures that are designed for a particular domain. They provide high performance due to massive parallelism. So here is an example that some of you might be familiar with. This is the Google's Tensor Processing Unit, which is for AI acceleration. And all it does is that it's a really huge matrix multiplication unit, right? So you can see the matrix multiplication unit over here. So all it really does is that it does a great job of doing the matrix multiplication. But you can do 64K of multiply per cycle. So that's massive parallelism. It's also low power because remember earlier, the hardware needs to kind of extract the instruction dependencies and so on and so forth. Here, there is nothing like that because you are doing a very specific job. And so you are very low power. On the flip side, this is very low programmability, right? So you can only run a particular application and you cannot really sort of execute many different kinds of applications on this architecture. So this is what is happening in the server space. Now let's look at what's going on in the embedded space, right? And in particular, one of the interesting points is the Internet of Things. So these are the devices that are collecting and sharing the data on the internet. And there has been an exponential growth in terms of the number of devices. You can see that, for example, 2025 projected 30 billion IoT devices. Now, initially, when the IoT devices are designed, they are actually collecting the data. So there are sensors collecting the data. They're sending the data to the cloud, and everything is getting processed in the cloud, right? So that's a very easy way of doing things. Now, it might not be a good idea to always send the data to the cloud, and it might be necessary in certain applications for you to move the processing from the cloud to the edge. Right? Why do you need to do that? So for example, here is a case where we want to detect if a person is falling down. This requires real-time detection, right? It's no good if you, for some reason, if the network is not working or does not have enough bandwidth and so on and so forth, you cannot really do this. So there are certain applications that require real-time deadline. Here is an application where you are collecting data about maybe your blood pressure or something like that. And again, there is privacy concern, so you might not want to send the data to the cloud, right? And so because of all these reasons, and sometimes you might not even have access to the network. More importantly, in terms of sustainability, edge computing is far more important than going to the cloud. And in fact, it can cut down the carbon dioxide emission by quite significantly by not transmitting the data, because transferring the data to the cloud actually takes much more energy than actually doing the compute in the device itself, and then only send sort of summary information to the cloud, right? So because of all these reasons, it does make sense for you to move the compute to the edge. However, if you look at the edge computing devices today, they are mostly very simple microcontroller. They work at ultra low power in order to save the battery life, but they have very simple execution models. So they're doing a fetch and then they decode and then execute. So this is a very, very simple, simple architecture, right? So these are using microcontroller, which are very different, which are actually very similar to the first Intel 4004 microprocessor that I showed you earlier, and very far from the AMD big devices that you saw. So the question is now, can I actually do edge computing on such small devices? And the answer is that it's really difficult if you want to do anything more than just the sensor data collection. So here is an example where we are kind of trying to do finger gesture recognition. So we are kind of trying to find out what, you know, is it like I'm trying to turn it around right side, left side, something simple, right? And this particular application, it's designed on a smartwatch using the accelerometer and the gyroscope. This case, in order to get things right, we need to sample at 128 hertz, which is the sample frequency of 7.8 millisecond per sample, right? And now if you try to do this using a very simple microcontroller ARM Cortex M3, which you can see over here, which is running at around 48 megahertz. And this is very typical of, you know, this kind of very simple systems, IoT systems. Then it takes about 577 milliseconds to process per sample, in contrast to what we require, which is 7.8 milliseconds. So we essentially, but of course, the power is very, very low. Now, if we can actually execute it on my mobile processor, which has a much more powerful processor, I can reduce the time to 13 milliseconds, but I still need a lot more power. So this is about half a watt, which is not kind of acceptable. So how do you do that? Okay, again, same, right? Instead of doing the generalization, you can actually do specialization. And indeed, at this point in time, AI accelerators is a very hot topic. So we have a number of startups that are coming up with AI accelerators for the edge. And I've just given some examples of that. But of course, you know, it's not just AI that you are going to execute on these IoT devices. So you can have certain other things which are not, you know, possible to execute because on an AI accelerator. As I mentioned, AI accelerators are very, very specialized. So here are some examples of, you know, so you can have other domain-specific accelerators. So here is one example. This is Navion. This is doing visual inertial odometry. So this is, and then this is BioWolf, trying to do a brain-computer interface. Now, all of these things are very low power, but they're designed specifically for one particular functionality. So what happens when you have, you know, a lot of different functionality? Now, of course, the watches today have become very powerful, the smart watches, and they are far more powerful than the kind of IoT devices that we are thinking of. So if you have a smartwatch like this, it basically uses sort of 2 generations ahead. The ones from 2 generations past, the ones that had been used in the phone. So for example, Apple iWatch is using the system that was there in Apple iPhone a couple of generations earlier, right? So this is the Apple Bionic SoC, system on chip, for the Apple Watch. And what you can see is that it has, you know, of course, it combines the generalized cores. So it has 2 big cores, 2 small cores, but it also has a lot of specialized units. So it has a GPU, it has a neural processing unit, it has other IP blocks. So by some estimates, there are at least 50 to 100 different IP blocks that are there. And it's not just, you know, Apple Watch. If you think of this is kind of really the embedded systems way of life. Any embedded system you can think of. You know, I have shown here different SoC, system on chip, and you can see all of them have like CPU, GPU, DSP, NPU, and then bunch of other IP elements, right? So this is what it is. And you know, these kind of systems, this kind of heterogeneous systems give rise to a number of interesting problems. For example, you know, how do you manage the power? How do you manage the temperature on this kind of systems? And you know, a lot of people have done a lot of great work on these topics, including some from my group, right? So this is a very interesting topic, and now one can also think of how do you actually do co-execution on such heterogeneous platform. How can you have an application that is taking advantage of many of these different cores in order to synergistically execute things? And again, you can get very good performance and energy efficiency out of it if you can map the right portion of the code to the right core. However, this kind of edge computing systems using heterogeneous SoCs is not feasible when we are talking about tiny IoT devices that has really low power and area footprint. So instead of watts, so if you think of these things, I can have 1 watt up to 2 watts, whereas I'm looking at milliwatt range when I'm talking about these kind of small IoT devices, right? So what we need is something that is not a complex system with many different accelerators. But then the question is, can I actually have just one accelerator that would be able to support multiple such systems? So let's look at a little bit carefully the trade-off between specialization and generalization, right? So what are the applications that can benefit from specializations? So of course, it has to be application that has enough parallelism. If your application cannot be parallelized, then you cannot get benefit from specialization. And then the computations roughly have to be stable and they have to arrive at regular intervals. So you need sort of kind of regularity. It cannot be very complex control flow because that's not really suitable for specialization. You also need relatively few memory accesses per computation. So that means that you need kind of memory locality. Otherwise, you are spending enough time and energy in getting the data from the memory to the chip. And so it's not going to be beneficial. So the good thing about specialization is that the applications that can benefit from specialization, they will do very well. But applications that are not benefiting from this specialization, they're going to suffer. More importantly, because any specialized IP can only execute a limited range of applications, when you create such a chip, you are actually you need many applications to use it in order for you to overcome the cost that you had in designing this system. So this is sort of a graph that shows that the trade-off between specialization and generalization. So on the x-axis, what you are seeing here is that how a specialized application, how much better it is compared to executing it on a general purpose processor. So right, so the higher the number, the better the benefit of this application from specialization. On the y-axis, what you are seeing is the production volume. So this is the number of units of this chip that needs to be shipped in order for you to benefit from the specialization. So when we were in Moore's law era, this is the light blue portion of the curve. When we were in Moore's law era, what was happening is that the general purpose processors were doing very well. So we don't need to. You cannot get much benefit from specialization. So either you need to really have a lot of parallelism, so the applications has to be high speed up from specialization, or they have to be high production volume in order for them to benefit from specialization, right? Or for us to make a case for specialization. Whereas we are now in kind of post-Moore's law era, where the general purpose processors, as I showed you earlier, is not doing so well. So the performance is not going up. And moreover, energy has become such an important factor in our design. So now you have more applications that can benefit from specialization. They may not, because generalization is not doing so well. So applications will have more speed up from specialization. And then we don't need such a high production volume for us to benefit from specialization. But you still have, part of these where you cannot specialize because these applications either don't benefit much from specialization, or you need higher volume. So the question is, can I actually try to specialize more applications which are in this gray region and in this black, dark blue region, right? So in order to do that, what you see is that I cannot have like lots of tiny specialized units, because I have sort of area constraint. I also have power constraint. So one of the options, and that the embedded systems community have looked at very for a long time, for almost 20-25 years now, is that how can we extend a general purpose processor core with domain specific functionality through what is known as custom instructions, right? And this has again come back in a big way through the RISC-V core. So what you are seeing here over here is a RISC-V processor. This is the original RISC-V core, and then you have an ISA extension, instruction set extension, where you have this accelerator where you can map new custom instructions. So these custom instructions, and then you can use them through a library from the apps. So what these processor customizations do is that they introduce instruction set extension for recurring computation patterns. So for example, this is your application's data flow, and if you find that this particular pattern is being repeated again and again and again, then what you can do is that this is your standard 5-stage pipeline. You can actually create a new instruction that encompasses this particular computational pattern, and then you can actually map that onto a specialized functional unit that can execute this particular custom instruction. So this way you can benefit significantly in terms of performance and power, because instead of fetching and executing 4 instructions over here, you are just fetching one big instruction with a much reduced latency. Now, this is one approach of getting the balance between the specialization and customization. And we kind of tried to do that for IoT devices by putting in this kind of small accelerators with each core. So these cores are very simple, code, like you can think of like ARM M3 sort of things, very small. And then we put a small amount of accelerator over here, or we even had like even tinier accelerator, and we were stitching together these tiny things together in order to create a bigger accelerator. And with that, we could kind of achieve, so for example, for that gesture recognition application that I talked about earlier, we could actually achieve sort of a 7.6 millisecond per sample processing time, which was good for us. But if you look at the power was 139 milliwatts, so which was not good for us. Okay, so then we started thinking about, can we design an universal accelerator, right? That is general yet special. That means that it is the same silicon, it's the same hardware, but we can use the software in order to sort of instantiate different hardware accelerators on top of that same silicon. And in order to do that, basically, you have to have 3 different things. So first, you need to embrace the parallelism, right? So because as I mentioned, that unless you have parallelism in your application, then you are not going to benefit. So you need to have parallelism. You need to keep the hardware really, really simple, right? Because you want to make it low power. So that's what we care about in edge computing. So you have to be low power. So the hardware cannot do a lot of complex things. It needs to be really simple. And then you have to expose things to software. So that's because somebody needs to do all the hard work. And then we are kind of moving that hard work from the hardware to the software, or in particular to the compiler. Okay. So now how do you do that? Now, one way of doing that is to move away from von Neumann computing model, which we showed earlier. So this is the stored instructions concept. You fetch the instructions, you execute the instructions, you also fetch the data, and then you do it like that. And that's inherently sequential. Instead, you move to the data flow computing model, which is inherently parallel. So that means that you actually extract all the parallelism. So you create a data flow graph, which is completely parallel with all the dependencies and everything. And then instead of having these instructions that are being stored over here, what you have is that you have actually mapped this entire data flow onto the hardware, and you have configured the hardware so that it can actually execute these things automatically, right? So basically what happens is that your data comes in, and then it reaches the first of these things in the data flow, and then it triggers the next one, and so on and so forth. So this is how this whole processing actually works. So instead of the stored instruction concept, you have the entire data flow being mapped onto the hardware. So that's the data flow processor architecture, and it's not a new idea because it has been there. It has been there from 1975, but it never took off. Why? Because the general purpose processors were doing so well, as I mentioned earlier. That fast forward 60 years, what we are seeing now is that data flow computing is everywhere. In fact, any of the AI accelerators you can think of, few of them are GPU based, but almost the rest, all of them are based on data flow computing model. So if you look at Cerebra, Sambanova, GraphCore, AMD AI Engine, all of them are doing data flow computing. Why? Because number one, the data flow computing really matches well with the AI sort of data flow in the software, and so that actually gives us huge performance and power gain, right? But then they are still designed for one particular data flow. Now the question is that how can we support different data flows on the same hardware architecture, right? Now that's where, so that's a long introduction, but that's where sort of coarse-grained reconfigurable array, or CGRAs, come in. They have also been called software-defined hardware by DARPA in US. Basically, the idea is that I have the same silicon, and then the software will instantiate the data flow corresponding to different applications onto this silicon, right? And the goal is that it should be as easily programmable as a processor. So if you think about moving from specialized ICs that I showed you earlier to the microprocessor. So now we are kind of saying that, can we actually have an accelerator instead of having these specialized accelerators? Can I have an universal accelerator that can actually accelerate all the different applications? And their performance and energy efficiency should be closer to domain-specific accelerator. Of course, it would not be as good as a domain-specific accelerator because it has, it's supporting multiple different things, but it should be closer to that. And that's where the coarse-grained reconfigurable array, or CGRA, comes in. It is the most promising realization of that software-defined hardware vision. And there are a number of companies that has sort of CGRA. So if you are using a Samsung mobile phone, then certainly it has a CGRA inside to support audio and video through the Samsung Reconfigurable Processor, or SRP. If you have, Intel has multiple patents on configurable spatial accelerator, which is also a CGRA. Renesas has the dynamic reconfigurable processor, and a bunch of other sort of startups also are using a CGRA. Right? So a CGRA is nothing but a very simple 2D array of processing elements, and we will go into the details of the CGRA architecture in a few slides from now. But this is just an overview to show you that you have the processing elements, and they are connected to their neighbors. The processing element is very simple, so you just have an arithmetic logical unit connected to the neighbors, and you have a configuration memory. This configuration memory essentially stores what you need to do, or we do kind of part cycle reconfiguration through this configuration memory. But of course, it's tiny, it's very small. It's not as big as a as a program. Now, if you look at this particular architecture, it actually satisfies the three things that I was talking about. First, it satisfies parallelism. It is an array of simple processing elements. It has very simple hardware. So you can see these are not cores. These are just simple arithmetic logical units. So it's very, very low power, and it's exposed to software. So, everything can be done by the compiler. So the compiler does heavy lifting of actually mapping things onto this particular architecture. Okay, so basically what the CGRS does is it combines the efficiency with the programmability. So if you look at the Google TPUs, for example, it's a specialized architecture. It can only do matrix multiplication. And it has been designed specifically for that. Whereas if you look at the CGRA, it can be configured in software to support a matrix multiplication, and it can do almost as good as as that, because it can create the same data flow onto this particular hardware. Okay. But the advantage is that in case of a TPU, you are only able to do the GEMM, or maybe you would able to do the convolution, but you cannot do the FFT. Whereas with the CGRA, what you can do, and this is an application, very simple, a TinyML application that's doing a speech recognition. It goes through an FFT, GEMM, and convolution kernels. And as you can see, we can configure the same silicon first to do FFT, then GEMM, then convolution, and then we repeat this process within the same application, right? So this is the benefit. And again, so the most important thing for the CGRA is, of course, you have to have the architecture and the hardware, but you also have to have the support of a very strong compiler in order to take an application data flow. So this is your processor, your application kernel, and this is the data flow graph of the same thing. So you find out what are the operations, what are the dependencies, and then what the compiler does is that it has the CGRA architecture, it has the data flow graph, then it does the placement and the route. So it first places the operations, and then it does the routing of the data from one PE to another processing element, right? So this is the placement and the routing are the two things that the CGRA compiler needs to do. Now, one of the things, and again, we will go into the details of how the CGRA compiler works, but one of the things that you can notice here is that this is a spatio-temporal mapping. What I mean by that is that it's not like I'm just kind of mapping the entire data flow graph into a spatial way, but I'm also doing the temporal. So for example, this particular functional unit is executing the operation N1 here, and then it's executing the operation N2 here. So which means that I'm actually doing a reconfiguration, a per cycle reconfiguration. So why is that a good thing? Because what happens is that if you have just spatial mapping, then you need a lot of area to do that mapping, right? Whereas if you are doing the spatio-temporal mapping, then you can have a much smaller area, and you can do time multiplexing to achieve the same operation. And as you can imagine that in embedded systems and IoT edge computing, it's very important for us to save both power and area. And the way you do this scheduling is through a concept called software pipeline. And again, we will look at it in more detail. But what essentially happens is that you can see that each of these is a one iteration, and you are not executing one iteration at a time, but you juxtapose multiple iteration. So for example, in this cycle, you can see we are executing first, second, and third iteration all in parallel. And so what is important is that what is the distance between two iterations? How fast can I actually pump a new loop iterations into this accelerator? So if I can do it per cycle, that means if this is known as the initiation interval, what's the distance between two iterations that can be pumped into this particular architecture? So if it is a 2, that means that every 2 cycles I can input a new iteration. Here I can input a new iteration every cycle. So of course this has a much higher throughput than this one. So our goal is to actually have as low II as possible, because that will actually give us the maximum throughput, right? Now, one of the things I forgot to mention is that remember that whatever I have this placement and routing, I need to actually make that I have to encode that within this configuration memory. Now, this configuration memory is small, so some of the architectures will have between 20 to 30 of this entries. So that means I cannot kind of have like really the whole application being mapped onto this thing. Instead, what we are mapping is the loops. Why? Because in the loop, as you can see that it's being repeated. So I just need to store the configuration for this loop body, and I can actually repeat it. So basically, the CGRA is essentially just map or accelerate the loop kernels, and that's perfectly fine because that's the portion where we actually spend most of the time. So then the question is, and this always comes up, how does the CGRAs compare with FPGAs, right? Because both are reconfigurable architecture. So what's the big deal? Now the FPGAs, as many of you might be familiar with, is that it's also achieved specialization through reconfigurable hardware, and there has been tremendous progress in high-level synthesis of applications onto the FPGA. But that being said, still high-level synthesis is complicated, and so for example, our group worked on how exactly do you decide on different parameters for high-level synthesis, how much loop unrolling should you do, how you should do the software pipelining, and so on and so forth. And it's not very easy for a software developer who has never touched a hardware to actually work with an FPGA, right? So it's challenging. Moreover, the FPGAs cannot provide you with a very high performance. It cannot provide you with a very high performance at low power, because you are doing a bit level reconfigurability. You are using the logic blocks in order to create even the ALU and simple circuits, right? Whereas if you look at the CGRA, we already have the ALU built in, right? So that actually gives us a much lower power compared to the FPGA, right? So the fact that the CGRAs offer word level reconfiguration, and that's where coarse-grained comes from. The term coarse-grained comes from. You are not dealing with bit level reconfiguration. You are doing with a word level reconfiguration. So that gives you the ability to do part cycle reconfiguration in the first place. It becomes much lower power, so it's much more energy efficient. It can also lead to higher frequency. Why? Because in case of FPGA, the high-level synthesis will decide what is the frequency at which you are running, and it's sometimes challenging even to reach 100 megahertz for a complex circuit. In case of a CGRA, as a software developer, you are not trying to figure out the frequency. The frequency is already existing, right, in the system, because it is a silicon, so you already have the frequency. So you are just doing a mapping. So in that sense, mapping on a CGRA is closer to a software developer mapping things onto an architecture rather than a hardware design, right? And so it's closer to, for example, VLIW architectures, if any of you are familiar with it, than high-level synthesis for ASICs and FPGA. So all that means is that CGRAs are easier programmability compared to the software developers. And I've already mentioned this. On an FPGA, you have to only map spatially. You can do dynamic reconfiguration, but you cannot do it every cycle. You cannot do it, certainly you cannot do it per nanosecond, because it's very, very expensive. Whereas in case of a CGRA, you are doing a spatiotemporal mapping, which means that it can be less area and less power. So overall, what happens is that compared to an FPGA, so these are like the energy efficiency, the improvement, and as you can see that the efficiency can be much better normalized with respect to FPGA. You can achieve about 75x, anywhere between 10x to 75x improvement in terms of energy efficiency. So so to conclude, what you have over here is that the CGRAs are really kind of combining efficiency with flexibility. So we looked at general purpose processors, which are highly flexible, can support any application, but they're not very efficient. We looked at ASICs, which would be very efficient because they are designed for a particular application. Similarly, sort of domain-specific accelerators, but they are not so flexible. The FPGAs are, more flexible than them, but they are also not efficient. So what we are trying to hit is the coarse-grained reconfigurable array, or CGRA, is the sweet spot between these places where you can actually have flexibility, but at the same time, they have to provide high performance with low power. So I'm going to stop here and just ask if anybody has any question before we delve into the details of the of the architecture and the compiler. Any questions? Please feel free to unmute yourself or put it in the chat. Okay, so since I don't see that, then I will pass the time to Thilini to talk about the CGRA microarchitecture.
Okay, hello everyone. I'm Thilini, fourth year PhD student at NUS. So I'll be presenting the next section in this presentation, which is the CGRA microarchitecture. In this section, we'll be talking about different components of the CGRA and different design trends. So to start with, we'll first see what is a CGRA. A CGRA consists of set of processing elements which are interconnected by a network, and those are connected to a data memory or an on-chip memory. So in the diagram here, you can see a 8x8 CGRA with like 64 PEs. Each PE is directly connected with its neighbor, forming a mesh network. And all the PEs at the two border are directly connected to a data memory where we store the any data incoming arrays and which will be forwarded to the middle part of the CGRA. A CGRA can be loosely or tightly coupled to a host processor. In this diagram, we can see it's connected to a RISC-V CPU through a controller. A CGRA being a passive device, it will always rely on the CPU to trigger the control. For example, at the beginning of the execution, the RISC-V CPU will send all the data required for processing to the data memories of the CGRA, and then it will trigger a start execution signal by which the CGRA will start the processing. After the processing, the CGRA will trigger the execution end. Then the CPU or the controller knows that the execution has finished, and it will start the data, loading the data back to the main SRAM. So the CGRA can be reconfigured spatially or temporally, as Prof. Tulika mentioned earlier. The main difference between CGRA and FPGA is its ability to reconfigure in both spatial and temporal domains, which means we can do reconfiguration in parallel with the execution. So this diagram represented a system on chip design with integrated CGRA, which is marked in this red box as space. Here it's a RISC-V processor again, but it has a lot of peripherals, SPI, I2C, UART and all, so that this can work as a standalone IoT device, which can be connected to different sensors like IMUs and all. Okay, moving on. Next is the processing element. It's like the basic block of the CGRA. It's a simplified version of the processor core, but with a very limited number of components. It will consist of a function unit. It is mostly a ALU, which is responsible for performing the computation. And it will be there will be some sort of interconnect which connects the processing element to the external PEs. So the interconnect will handle any incoming data from outside PEs, and it will forward the data to function unit. And once the computation is done, it will take back the data and send it to the neighboring PEs. Next important element is the configuration memory, which handles all the reconfiguration. So whatever the compiler determines schedule is stored in the configuration memory, and during the execution, the function unit and the router or the interconnect will be reconfigured based on what is stored there in the configuration memory. There is also some sort of local storage in the PE to store any intermediate data. This is a special PE where it's a standardized interface presented in SNAFU CGRA paper. They present a processing element which can be bring your own functional unit kind of design where you can have custom function units connected to this standardized interface. But if you see the components, there is a configuration part, there is a router or the interconnect part, and there is a functional unit and some storage. So its basic components are pretty similar. Next, we'll move on to the function unit. As I said, function unit will perform all the computations. This is an example of function unit which has a ALU and a multiplier. Usually there are 2 or 3 inputs with predicate, and the input can be coming from external PEs or from a constant stored within the PE. And the reconfiguration of the opcode is done through the configuration word. The table shows a list of opcodes. It comprises of very common opcodes like addition, multiplication, some logic operations, comparators, and all. So various designs have various configurations. They choose to be 16-bit, 32-bit, 64 bits, either fixed point, int, float. So it's all depending on their requirement. And there can be single cycle operations as well as multi-cycle operations. And usually a predicate mechanism will be there to handle any branches. And if the PE is directly connected to the memory, in addition to the arithmetic logic unit and multiplier, there will be some sort of memory handling load store unit, which will perform memory operations like load and stores. So we'll see what type of functional units are there in the state-of-art CGRS. First is there's a variation of homogeneous and heterogeneous functional units. For example, in this EGRA design, there are like ALU functional units and separate multiplier functional units. Also in the second figure, which shows address architecture in a heterogeneous version derived from a revamp tool, which is a heterogeneous CGRA realization tool. There are like multiple function units with subset of operations which are diverse across. And there are functional units with different precisions. For example, transpire functional units has floating point unit, and there is also a divide square root unit. So along with the ALU, so this also creates a heterogeneous set of functional units, but with different precision levels. To improve the power, there are designs with approximate functional units. For example, this XCGRA, which introduce a quality scalable ALU. Depending on the required accuracy level of the application, you can like change the amount of the quality of your result depending on some statically designed schedule. Also, there are SIMD functional units to improve the performance, power efficiency and performance, basically, where you have multiple SIMD lanes, like multiple parallel functional units which acts as multiple SIMD lanes. For example, it's in the Healware CGRA. Next component is the interconnect. Interconnect is responsible for connecting the internal and external data path. The majority of CGRA designs have NOC-based interconnect. In this type of interconnects, the data can either bypass the ALU and like go through the router without going through the ALU. So a PE with this type of interconnect can act as a router only processing element as well. So in this NOC type of architecture, there's usually a crossbar design, which is connected to external and internal ports. And these crossbar configurations are determined again by the compiler. So it's very simple. Everything is like stored in the configuration memory. At the runtime, you just configure your crossbar so that your connections are made and so that the architecture is kept simple and area efficient and power efficient. And older CGRS had a neighbor-to-neighbor type interconnect, which is even simpler, but the data has to always go through the functional unit to go to the next PE. So in this type of architecture, there is like a limited routing space. So there will be a lot of congestion. So if you look at the state-of-art CGRS, they use different type of topologies. For example, mesh, extended mesh, torus, circuit switched mesh. For example, in Riptide, they use switched mesh where the router is outside the processing element and it will be connected to multiple elements. For example, a router here will connect to adjacent routers as well as it will connect to all the adjacent PEs, creating a very high routing space. And in HiCube, there is a mesh interconnect where only the neighbors will be connected physically. And in Morphosis type of architecture, there's like an extended mesh where apart from the physical neighbor connection, there is an additional physical connection connecting all the elements in a row or a column. So going a bit into HiCube, it proposes a special type of interconnect, which is single cycle multi-hop type interconnect. What this interconnect does is that it creates a large dynamic neighborhood so that like any two P's can be reached within single cycle by asynchronously bypassing intermediate P's. For example, if you take this DFG, in a HiCube-like architecture, you don't need to place the nodes in very close by PEs. It can be placed a far away PE so that it can still reach the destination in a single cycle. If we look at this with the example, suppose for this data flow graph, it is placed on a generic architecture. If you want to send data from node 1 to node 4, you will have to go through a routing phase and register phase. That means the data will first go from here to the adjacent PE, get stored there one cycle, and then it will go to the PE where the computation will happen. But in case of the dynamic, like the neighboring space created by HiCube, it can be achieved in single cycle, drastically improve the performance. If you look at the interconnect of HiCube, it's just there is a bypass path added closer to the outer, like incoming ports of the PE, so that the compiler determines whether to bypass or to register the input. So this link is configured by the compiler, and the number of hops is also a compiler parameter. So in our experiments, it shows that in HiCube experiments, it shows that a 4 hops path is sufficient for most of the applications, whereas this type of like smart knock can go up to 13 hops. So this HiCube CGRA was fabricated, and this photo shows the results, and it was connected with a TI sensor tag through a SPI interface so that it will form a complete system. So this HiCube achieves 90 MOPS per millibaud at TSMC 40 nanometer, which is competitive with respect to most of the FPGAs, ARM CPU, and SRP CGRA by Samsung. Next, we'll move on to the on-chip memories. So there are two types of on-chip memories. One is the data memory, and the next is the configuration memory. The task of data memory is to store input and output data arrays, which will be used in the computation on the CGRA. So this data memory can be centralized or distributed. This figure shows architecture with centralized SPMs, where the data memory is global and only few PEs can access it. The plasticine design, which is again a CGRA design for parallel patterns, they have a distributed sort of memory architecture where the pattern memory units, so the PMUs are distributed across the PE array so that more PEs can access them. And also we can distinguish data memory designs with coupled or decoupled address generation architectures. In a coupled a CGRA with coupled address generation of the elements will happen on the PE array, but in a decoupled scenario, there's a separate unit to perform the address generation, and the PE array will only handle the computation. So Cascade proposes such decoupled access generation CGRA, where it has a stream engine unit and stream registers to do the access beforehand, and the stream registers will feed the data through as streams to the PE array directly. So it separates access and the execute part of the data memory. So, if you see an example, DFG, usually the majority of the portion is used in that address generation. For example, in this DFG, you can see like 6 nodes are used for the address generation and only 4 nodes are for actual computation. So if we execute this whole thing on a CG array that is in a coupled fashion, that means it will take a lot of time. For example, initiation interval II here is 3. And if you do this on a CG array like Cascade, it will save the resources for actual computation, and II will drop to 1. So this II, or the initiation interval, is like the performance metric. If it is lower, it is the better. So we can say that this type of decoupled architecture will improve the performance. Next, we'll move on to the configuration memory. As I said earlier, it will store the compiler determined schedule. So this also has either centralized designs or distributed designs. This XCG array has a like global configuration memory, but in this type of design, we need to make sure this is accessible as fast as possible. Otherwise, there will be delay in accessing the configuration memory, which can affect the performance. So in HiCube, there is a distributed configuration memory. Each configuration word is 64 bits, and there are like 16 entries. So whatever the application kernel that can be mapped within 16 entries can be fitted on HiCube. So this diagram shows an example configuration word. If you see the sections, this part represents the router configurations, and the bypass, this is correspond to HiCube. So this is the bypass part, and the remaining part is for the LU opcode and any constants. So this if the configuration memory is like can be read in every cycle, so that it is pipelined with the execution, and so execution and reconfiguration happen in parallel. Another class of classification is based on the execution model of the CG array. We can classify as spatial and spatio-temporal CG arrays. In spatial CG arrays, what they do is that they reconfigure the PE array once, and then they execute for the whole set of element here n, and then it will move on to the next. So the problem with this type of architectures is that to fit a bigger DFG onto a smaller graph, you might need to partition the DFG so that you can map each of these partitions spatially. But in contrast, a spatio-temporal CGRS take the whole big CGRA, whole big DFG, and map it onto the CGRA where the II will be bigger than 1. So main difference is that the spatial CGRS consume low power mainly because of the less frequent reconfigurations, but they might suffer from performance. But the spatio-temporal CGRS give better performance, but at slightly higher power budget. So in the literature, there are multiple CGRS in both categories. For example, Soft-Brain, Riptide, Snafu, they all follow spatial execution, while HiCube, Transpire, they follow spatio-temporal execution. So being a software scheduled machine, CGRA architecture is quite simplified. So if you look at the design space, you have the PE function to vary it. So it can be either LU, custom block, or lookup table, and the interconnect topology can be crossbar, mesh, NOC. Reconfiguration can be either static, dynamic, and you can do either partial reconfiguration, full reconfiguration. And for the memory system, you can do a cache-based system. There are also some CGRA designs that use PIM, processing in memory. And For the communication, there can be a register file, FIFO, so on and so forth. And for the interface, it can be like loosely coupled with the processor, or it can be tightly coupled. And CGRAs are used as co-processors. And for the PE control, it can be distributed or centralized. And the main controller can be a general purpose processor, VLIW core, and different things. So this covers pretty much the design space of the CGRA, and the various designs follows various design points in this design space. So if we look at the trends, so there are like multiple works focusing on energy optimization. So how to bring down the energy so that this can be applied to ultra low power sensor type of scenarios. And one major issue is how to handle the memory bandwidth, because like transferring data from host processor to CGRA might take long time. So you might want to be efficient in that case. And there might be different memory managements internal to the CGRA also. And also there are like different execution mechanisms like the SIMD, VLIW. So all of them is targeted for either performance or power efficiency. So next we'll show a little bit about our own CGRA PACE. This is a SOC. It is a RISC-V core combined with the 8x8 CGRA. As you can see in this diagram, it has a very tiny footprint, 4 millimeters by 2.5 millimeters. So this achieves 582 GOPS per watt at 0.45 watt voltage in 40 nanometer ULP. So this is around 1.1 milliwatt power, which is very low at 10 megahertz. So this is estimated to go till 1 TOPS per watt at 22 nanometers. The PCB here shows the IoT system where the processor is placed in the middle and you have all the peripherals, as I said, so you can use this as a standalone IoT platform. So into the details of the architecture, if you see the layout, there is a external memory, SDRAM memory, and there's some on-chip SRAM as well. So in the fabric, majority of the portion is taken by the SRAM as usual. And apart from that, there's half of it is base core, in which you have the dual port memories on the sides. And in the PE array, you can see there's also a local memory, which is the configuration memory, and router and ALU. So this table summarizes where our design pace stands in terms of the rest of the CGRA architectures. There are like plenty of architectures in academic and commercial. Most of them are done till post-synthesis simulation, post-PNR level, but there are few that goes up to silicon. So if you compare and place pace among these CGRAs, you can see that it has a competitive power efficiency of 582 GOPS per watt, which is like competitive with the Amber CGRA at like 40 nanometer. So that's all for this section. So if you have any questions. Next, we'll move on to the compiler section. Join will take over. Thank you very much.
Hey everyone, this is Joy, a final year PhD student at NUS, and I will join as a research fellow as well. So I'm going to introduce the CGRA compilation. So as we all know that CGRA is a very high reconfigurable architecture. So the CGRA compiler is very important for the CGRA to realize its potential. So CGRA targets computer-intensive kernels such as convolution, FFT, and video process kernels. And so the host processor, it means the CPU needs to transfer the data to CGRA and configure the CGRA and invoke the CGRA. So this is the application example. A typical convolution neural network has a convolution fully connected layer and a softmax. So a convolution and a fully connected layer are target kernels for CGRA. For a fully connected layer, for example, we can get the source code. It's a 3-level nested loop, and we can use the data flow graph DFG to represent it. And to compile the whole application onto the CPU plus the CGRA, so we can generate the C source code and identify the target kernel for CGRA, that is convolution and fully connected layer. And we can use the LVM compiler and to compile the normal code like softmax or some other inputs pre-process or post-process. And for the target kernels, for convolution and fully connected layer, we use CGRA compiler to generate the binary for CGRA and the CPU. So the CPU will invoke the CGRA to execute the target kernel convolution and fully connected layer, and also try to like send the configuration to CGRA, invoke it, and get the data back to complete the whole flow. So if you have any question, you can feel free to interrupt me or post in the chat channel. So as we all know that CGRA target computer intensive kernels, mostly they are loops. So the main problem in the CGRA compilation is to map the loop. So for example, this is the kernel code, a simple loop, just one level with like one with 3 field array, and with one in each iteration we have one add and one multiply operation. So first we generated the data flow graph, it means the DFG. So we have to load the operation to load the BI and the CI, and we have one add operation to add BI and the CI, and also a multiply to multiply AI and the CI, and a store operation to store DI back to the on-chip memory. Note that this DFG is to describe the single iteration execution. So let's just, for example, we have 1/4 CGI. It means that we have 4 PEs, and the process to compile the DFG onto the CGI is called the mapping, and the mapping is to place the DFG nodes onto the spatial temporal PEs and route data dependency. For example, so let's say we have 1/4 CGRA. We can draw the schedule. First, at the cycle 0, we execute the iteration I, and we place node N1 here, and we can place N2 here because there is no data dimension between N1 and N2. So next, to place or execute the node N3, so we need to route data dependency through the on-chip network. And then for the node N4, we place it at cycle 2 at PE2, and route data dependency through the on-chip network. And at cycle 3, we still place N5 here to execute the next iteration I+1. Actually, we don't need to start at cycle 4. We can start at the cycle 2. So it means like at cycle 2, we can execute node N1 and N2, and cycle 3, we execute N3 and N4. Meanwhile, we start, you can find that the time difference between iteration I and iteration I+2 is 2 cycles. So cycle 0, we execute I, and cycle 2, we execute I+1. So at cycle 4, we will execute the next iteration of N1 and N2. So actually, it will lead to a steady state. It means that, for example, every 2 cycles, we repeat the same execution. So in CGRA, it's called the initiation interval. That means IR. So you can find that here the IR is 2. It means every 2 cycles we repeat the same execution. For example, at cycle 0 we execute N1, N2, and cycle 2 we execute N1, N2, and cycle 4 we execute N1, N2, cycle 1, N3, and cycle 1, N3, and cycle 3 we execute N3. So it's kind of repeated schedule. So given the schedule, actually it's a generator schedule called a modular schedule. It's repeated every 2 cycles. So the thing is that to generate such schedule, we can generate the left side modular schedule, so it will lead to a left side the whole schedule. It will automatically generate a schedule. So and the modular schedule IR is 2. So for the for example, for one PE that we have the configuration memory. The config, as I mentioned earlier, the configuration memory will store the modular schedule. So for example, in each PE, it might store in the second PE, it will store N2 and N3. Next cycle, it will store N2 and N3. So the configuration memory, for example, it has 24 items in our HiCube. And for this example, we just have each P just need to execute 2 items, right? So it will not fully utilize the configuration memory. So hence that for each P, the maximum items or its maximum operation is 24. So moreover, if we can find the schedule, so every 2 cycles we can execute the new iteration, and it means that this is 2 is the IR value, right? So if we have a different IR value, let's say 1, it means 1 cycle. Every cycle we can start a new iteration. If we have IR is 3, every 3 cycle we start a new iteration. So the logic here is that the lower the IR, the higher the performance. So and so because that we have 24 items in the configuration memory, so the maximum IR we can achieve with that 24. Another terminology in CGI compilation is called MIR. MIR is the theoretically minimum IR. So MIR is decided by the resource minimum IR and the recurrent minimum IR. So for example, we have a DFG. It's similar like the previous one, but we add a package here from node N5 to node N3. So the package here is that the data dependency is a cross iteration. For example, in current iteration, we execute N5, but the next iteration N3, the N3 of next iteration will need the data from data of N5 from the last iteration. So this is called a package. So to calculate the resource minimum IR, so let's say we have a 1/4 CGI. It's very simple. It's calculated by the number of nodes by the number of PEs. In this case, we have 5 nodes and we have 4 PEs. So the resource minimum IR should be 2. And we have recurrent minimum IR. So let's say, for example, we just draw the part of N3, N4, and N5. And to execute the next iteration of N3, N4, and N5, so we need to route the package data dependency, right? So it means that the distance between N3 and the next iteration N3 is 3. So the mean distance is 3. Actually, it decides the recurrent minimum IR, right? Remember that the IR value is that the number of cycles you start a new iteration. So to execute the next N3, node N3, right? So we need to wait 3 cycles to get the data of N5 to execute N3. So here the recurrent minimum IR is 3. So if you have any question, just ask me. So So next slide is that once we for DFG and for CGI, once we generate the MIR, for example, MIR is 2, and we start to map. For example, for IR2, we can generate the modular routine resource graph. So here the modular routine resource graph is kind of time extended resource graph. So let's say we have a 1/4 CGI that as IR2 will replicate 2 times and connect the create the connection between that time spatial temporal PE. You can see right here from the PE1 to the next cycle, PE2, PE1, we will create such kind of connection. And also from the current, from the second cycle to the first cycle of PE, we will also create some connection because of its modular, it's repeated execution. We execute the first cycle PE and the next cycle PE and then first. So because it will be a modular routing resource. So after creating the modular routing resource graph and given the DFG nodes, we will try to place the DFG nodes onto some onto the node of PE modular routing resource graph and use the edge in the modular routing resource graph to route the edge in the DFG nodes. So we can generate a modular scheduling, right? So however, it's not always possible that given an IR, we can generate a feasible mapping. If we can't generate a mapping, so we will increase the IR until we exceed the maximum IR. So next cycle, next iteration, we will try to use the IR is 3 and create replicate 3 times. If not possible, we increase to 4 until remember that for our high cube we have 24 items. It means that we can the maximum possible IR is 24. If we can't get a mapping within 24, so it means we can't map the DFG with this CGI8. So the whole mapping process involves the place the DFG nodes and routine data dependency. However, you can see that for each DFG node, we can place on any spatial temporal PE given this example. And it means that it has multiple placement candidates. Then how do we choose them among these candidates? Or, for example, we place N1 and N2 first. Actually, this placement choice will affect the mapping of N3 and N4 because of data dependency. So how to quantize this kind of effect? So we need to solve this kind of problem in our mapping to achieve a high quality mapping. So I'm here to introduce a simulator annealing algorithm that I guess you might be very familiar. So simulator annealing is a meta-heuristic algorithm which is used in in a lot of like scheduling algorithms such as task graph in multi-core CPU or any other like job or selection algorithm. Here, it's also a popular algorithm used in CGI mapping. So in CGI, we first generate an initial mapping. I mean, in each IR, we generate an initial mapping. It's usually invalid. For example, you have some congested routing, or you have some nodes it's not can't be mapped. But don't worry about this. We will try to do multiple iteration or move. I mean, remapping some nodes and reroute some nodes, and try to find a valid mapping. So here to generate the initial mapping. So for example, still this DFG example, N1, N2, N3, N4, N5. So let's say, and we have 1/4 CGI, and we have a modular routine resource graph with IR is 2. So first we can place N1 here, and the next cycle we can place N2 here. I mean, you can place randomly, or you have some cost function to guide it. And for node N3, Please note as we have placed N1 and N2 here, we need to route data dependency between N1, N3, and N2, N3. Of course, we can go through all the other PEs to check other PE whether it's possible, or we can directly select this PE. Anyway, we go ahead and for N4, we place here and we try to route data dependency from N2 to N4 and N3 for N4. For N2 and N4, just directly route it. However, because of limited resource, and there is a congestion in the routing. That means that N3 and N4 use some other routing resource. It's being used by other DFE nodes. So, but remember that like initial mapping can be invalid. So don't worry about it, and we try to solve it later. And now we go ahead. So for node N5, and we try to route N4 and N5, but unfortunately we still got a congestion. So this is the initial mapping, and we can see that there are two DFG edge got congested. And we will try to do multiple iteration or remapping to achieve a valid mapping. So this is the initial mapping, invalid mapping we just generated. And so the simultaneously, as you can see from the text, so it's annealing right. So it's from high temperature goes to low temperature. And at each temperature, there will be multiple movements. So we just say movements. What is a movement? So a movement is that select a random DFG node to unmap. And for example, in this initial mapping, we select the node N5 and select a random PE to map the operation. For example, select N5 and it goes to here. Because the placement changes and we need to reroute for node N5. So we route here. And because we move it, it's a different mapping and routing. But this time we got the congestion between N4 and N5 disappears. So it's much better. It's better than the initial mapping. So if this movement we route it and we achieve less cost, so we can directly accept the movement. So the cost means that the mapping cost is defined by the user. I mean, you can customize it. So for example, the cost function can include such as like a number of unmapped nodes or number of used resource and the number of congested routing. So however, I mean, it will go like a multiple iteration in its temperature and go multiple temperatures. However, this like kind of movement, this kind of strategy will cause a problem called local minima. So what is the local minima? For example, let's say you have a starting point, you have a relatively high cost. So we try to optimize use some like a random movement. Once we have the less cost, we accept the movement. However, it will cause a problem called local minima. And let's say we have a point called the global minima. So because that we have a local point minima and it's we get stuck here and we can't because we always accept good movements. And I mean like a movement called less cost. So we got stuck here. We can't go out and go to achieve get to global minima. So it means sometimes a movement leading to a higher cost can also be accepted. Okay, so the chance to accept here is defined by a probability function. It's relevant with delta E. Delta E means the cost change. So if, for example, we have less congestion, the cost will be less, right? So it will be a positive value. And the T is the temperature, K is some like a parameter you customized. So if the P value is bigger than 1, we accept it. If it's less than 1, it means the possibility we accept it. Because a movement that leads to less cost is always a good movement. So we always accept a good movement. Sometimes it's possible for us to accept a bad movement. So because it's relevant with the temperature, and the higher the temperature, the high chance the one bad movement can be accepted. For example, this figure shows that so with so many number of iterations, the possibility of accept to accept a worse movement. For example, so with more and more iterations, the temperature will go low, so there will be less chance. Clearly, there is a less chance for us to accept it. So this is kind of the way how simultaneously to overcome local minimum. So if you are interested in it, you can check the reference here and get into more details. So after so many iterations, we try to generate a valid mapping. However, there is a disadvantage for such mapping. As you know, it's random optimization, right? We don't know where we will go, and it can handle some simple data definition, but it's very hard to map a complex DFGs. For example, this is the DFG example. So this dotted circle means that this is a complex part of DFG. You can find, right, this kind of like a relatively complex data definition from D to I, E to I, B to I, right, is much complex than the left part. So this is a mapping example, field mapping example without any DFG structure knowledge, right? So we human can know that this is a complex part, but however, the mapper doesn't know this is a complex part. So it just put nodes at the root, because when we place B, we don't know what happened will in the next. So we just place here, but this kind of placement will lead to a congested routing or a failed routing, we call so. So because it doesn't have a global view, knows that this is a complex part, so it can't well handle this kind of data definition. Let's say we know some like DFG structure knowledge. We know this is a relatively complex part, so we will not place B at a current location. Actually, instead we'll place B here, because compared to current previous location, this B clearly have more routing resource. So I know B has a lot of children or grandchildren nodes. So I will prefer to place B at this PE, which has more routing resource. Moreover, I know E will have more like complex definition, also move E from here to here. So with such kind of DFG structure knowledge, we can place and map the DFG in a global view. And of course, it's clearly it's much better without. I mean, if you don't know anything about the DFG structure. So the problem is that how do we generate the DFG structure knowledge? Here our work is that we call something a label. So label is something information that you on for the DFG nodes and for the DFG edge. So label describes the estimate the mapping distance among the DFG nodes. And we use these labels to guide the nodes placement. For example, we still have this kind of routing modular routing resource graph. So we just place B here, and when we place F, so we can refer to the label information. Label information shows that the mapping distance among DFG nodes, the temporal mapping distance or spatial mapping distance. For example, we check the information here, and we see at the recommended mapping distance is 1, spatial is 1, temporal is 1, so we can place here. So how to generate such DFG, such label information to guide the mapping? We used the graph neural network GNN to derive such information. So graph neural network, I think all of you know the neural network, but a graph neural network is a special neural network that's designed for graph. So it can traverse the graph to generate information for nodes and edge. So note that DFG is a data flow graph, so it's naturally suitable for the graph neural network to analyze, to generate some information we want. Graph neural network here is like it's very similar to what we learn in convolutional neural network or deep learning. It has some graph convolution given a DFG. It can generate some node or edge information we want. So this is done by our work in HPC 2022 LISA graph neural network based polymorphism on spatial accelerators. So if you are interested, you can check the more details or discuss with me. Another problem is the scalability. You can see that existing work they can handle the normal DFG like with 50 nodes with 100 nodes, they can handle it. However, for some like extremely complex thing, it might have 200 nodes or 500 nodes. How do we handle this kind of stuff? Here shows two examples that how we scaling the data flow synthesize on CGI. So the first we use multiple abstraction to divide and conquer. That means that given a very complex DFG, we can like partition the DFG or partition hardware to generate some middle level to simplify the problem. Or for example, in here in the source code, it has multiple levels, and we can partition something from the middle level and try to simplify the problem. And because there are some reused common patterns, for example, there are some in each iteration they have some repeated execution. We can reuse this and map to create a much hierarchical mapping. And in the second, as we say, we can cluster from the data flow graph level and also architecture level, means that we partition the DFG and also we partition the CGIA and then try to use the cluster level mapping and merge them to map them together. So actually, this kind of strategy is very, very effective. It can achieve some dramatic improvement. It can achieve like 17 times performance improvement and 5 times better energy efficiency. And for the compilation time, for example, for the 64 by 64 CGIA, the previous compilation time might take days to compile. Yes, take days to compile. But now it just take 15 minutes to compile the complex DFG. So you can check we have open source code. You can check the source code here and to get more details. So mapping approach. Here we have introduced some mapping approach here simultaneously, and the graph neural network one, and some like the divide and conquer approach. So totally we have some like integer linear programming ILP. I know all of you know the integer linear programming. It's quite a standard way to solve problems. But actually, because that it's an NP-hard problem and which there are a lot of constraints in the mapping, so ILP can achieve some good results on simple case, but very hard to map given the relatively complex DFG and architecture within reasonable compilation time. And also meta-heuristic, for example, we introduce simultaneously. And the heuristic one, it's optimized for each hardware. And machine learning based, like we say, graph neural network, there are also some work based on reinforcement learning or convolutional neural network. Also, we propose here are some future directions. If you are interested, you feel free to discuss with us, and maybe we can explore together. So the one problem is that how to replace the data for multiple level memory organization. Remember, we have some like a memory on chip memory, right? So if it's a bigger CGI, we will have a central SPM and some distributed on chip memory. And DRAM, for example, given a convolution neural network, it has a lot of data input, and we can't feed all the data in the central PM and distribute the on chip memory. And we need to keep some data, most data on DRAM. So how do we generate a feasible data placement pattern to get the global optimal performance and to swap in the data, swap the data in and swap data out? So this is a quite interesting problem, and is that it's possible to generate a comparable performance compared to ASIC accelerator. You know that deep learning accelerators are very popular, and CGI is a very universal accelerator and can achieve most a lot of computer-intensive kernels. How it compare with this kind of Google TPU, this kind of specific ASIC accelerator? Can we optimize the compiler and the architecture while didn't lose the generality? And how do we optimize for machine learning application and large graph model, large language model, right? ChatGPT is very popular these days, and there are some examples to run large language model on your mobile phone, right? In your mobile phone. So it's possible that we leverage the characteristic of CGI to run the LLM, large language model, in our CGI. So okay, thanks you. I guess that's all for my part. I will pass it to DMD.
Hello everyone. I'm Dhananjay. I'm also a research fellow in NUS at NUS. So I will be explaining the CGRA software toolchain. So as you have seen, the CGRA has a huge design space in terms of architecture as well as in terms of compilation algorithms. So in order to explore this design space as researchers, we can come up with a better designs which has better performance or power efficiency or flexibility. So in order to explore this design space, we need software toolchain. So let me first explain what are the software toolchains that are available open source at the moment. So these 4 toolchains are kind of prominent toolchains that has been used in CGRA research. But like all of these toolchains has a main drawback is that they are not truly end-to-end toolchains, which kind of missing critical components of the design process. For example, CGRME, they provide architecture W CGRA mapping with multiple mapping algorithms, but this only supports simple kernels, and also their compilation time is much longer for the complex kernels, and also they don't support like architecture modeling in terms of the memory modeling, and also they don't have the open source tool for verification. So likewise, most of these tools have their own strengths as well as kind of drawbacks. So in order to overcome these drawbacks, we basically in NUS we developed this toolchain called Morpher. So Morpher toolchain basically is a fully automated toolchain and which provide end-to-end CGRA compilation, architecture generation, and simulation. So it provides a flexible architecture specification language so that users or researchers can like describe their architecture in a higher level language based on JSON format, and also it provides application mapping, like multiple application mapping algorithms that's being discussed, and it can support complex loop kernels with control divergence and also recurrence edges without being limited to simple application kernels. And the toolchain can automatically generate the RTL or Verilog RTL based on that high-level abstract architecture model, and it can do cycle accurate simulation and also validate the compilation results as well as the architecture automatically. So this toolchain is open source. You can scan this QR code in order to locate the repository. So let me go into the details of the toolchain. So these are the main components of the toolchain. So this yellow components are the inputs. So we have 3 inputs. I will go into the details of them. And gray components are the intermediate results, and the blue components are the main functional components in the framework. So, so as I mentioned, there are 3 inputs. The first input is the application loop, application source code with annotated kernel. We are using this kind of annotation string in order to annotate the target loop. So here we have simple application kernel as example, the array addition kernel, which add 2 arrays and stores into the C 2 arrays in A and B, and stores the results into C. So the second input is the abstract architecture model. So abstract architecture model. So we have our own Morpho architecture description language, which is based on JSON. So basically, the architecture description language, we have these components, like basic components like ALU, configuration memory, and switches and registers. The architect just like user just need to describe the connectivity between these basic components in order to generate their own architecture, and also not only within the processing elements as well as the interconnect between the processing elements as well as the data memory connectivity can be expressed using this architecture description language. And also we another input is the basic modules. The more detailed implementation of these basic modules we provide in our toolchain. We provide a chisel-based implementations for these basic modules like ALU, switches, and register files. And users can also add their own basic modules if they wish to have more like optimized versions of the architecture. So by taking those 3 inputs, basically the DFG generation unit is generate the data flow graph of the application kernel, and also it generates the SPM data layout by assigning the loop arrays into the data memory. And by taking this data flow graph, the SPM data layout as well as abstract architecture model, CGRA mapper maps the data flow graph onto the CGRA architecture and generate the mapping configurations, where each configuration is configuration represent the configuration word that is going into the CGRA configuration memory. And also we have the architecture interpreter and auto generator, which generates the Verilog RTL based on the architecture abstraction model and the basic implementation of the basic modules on with Chisel. And using this Verilog RTL mapping configurations, we can do the simulation, and also we generate the test automatically. This data generator module basically extract the test data which is needed for testing or verifying the application application execution. So the data generation module automatically extract live in data which goes into the CGRA memories, and also the live out data which is the expected results in order to do the verification. So basically, using those intermediate results, we can do the C++ simulation, when Verilator based simulation as well as FPGA emulation. So I will go into I will demonstrate our open source artifact using this video. So here we have the one of the input is the architecture description. So this architecture description is based on JSON language, and you can see that the architecture is described only on very high level. And the other input is the application source code with the annotated kernel, as I mentioned earlier. So this is the application kernel that is going to be mapped onto the CGRA. And the whole toolchain is automated, so you need to only run this Python script, giving the input as the kernel. And it will invoke all the tools. First DFG generation, test spatial data generation, and it starts the CGRA mapping. And you can see like after a few seconds, it will generate a valid mapping. Yeah, so after generating the valid mapping, it will generate the architecture, the RTL or Verilog RTL of the architecture. And also it will invoke the Verilator simulation to verify the architecture, generated architecture, as well as the compilation binary. So you can see here it shows the memory content after the simulations. You can see there are like no mismatches from the expected results and what is generated by the simulation. So this in this folder, it will generate the Verilog file as like Verilog file of the architecture, and also we provide the VCD based simulation waveforms. It's also automatically generated, so you can go through the modules like the LUs and see what is happening at each cycle in order to do detailed debugs. So that is the simulation waveform. So this whole tool is available on in GitHub. You can use this QR code in order to locate the repository. So here are some results of the mapping quality and compilation time of our toolchain. So we have compared with the CGRME because that is the only open source framework that is available, which does the architecture adaptive compilation. So in this case, we have a 4x4 CGRA and interconnected in end-to-end neighbor-to-neighbor connections, and each V has a register file with 4 registers. So we have used the Polybench benchmark suites, the kernels from Polybench benchmark, and you can see the Morpher achieves the quality of mapping is the minimum II divided by achieved II. So which means the 1 means it achieves the minimum II. So Morpher was able to Morpher achieves the minimum possible II for all the kernels, and while CGRME failed to do so for 5 kernels. And in terms of the compilation time, Morpher is 13.3 times better or faster than CGRME on average. And also, as I mentioned, so our toolchain can map complex loop kernels rather than being limited to simple kind of loop kernels. So we have mapped these machine learning based kernels using Morpher. So one of the main so here we have results for 2 main kernels used in machine learning. One is general matrix multiplication and also the convolution kernel. So we can apply different loop optimizations, higher level loop optimization with and use the Morpher in order to map these kernels onto the CGRA. So you can see the GMM computation. We can, if we have an 8x8 CGRA, we can basically partition the GMM computations into multiple partitions and map each of these partitions onto the CGRA. So while mapping these partitions, so this is the loop kernel, the C code of the GMM kernel, where you have like 3 for loops, and we can map it as it is by kind of annotating this inner loop as the target, or we can unroll the loop. By unrolling, we basically kind of combine multiple iterations into one iteration, so that our like loop invocation overhead becomes less, and also it helps to improve the utilization of the CGRA. And also we can apply the coalescing techniques, which basically kind of remove the nested loops and like combine those nested loop into one loop using the control flow like if and else statements. So you can see here in when we apply these optimizations, we can obtain speed ups going up to 3.5x for gem unrolled and coalesced kernel, and also for the same optimizations, convolution can get 25 times better performance using those optimizations. So you can play with these different optimizations and map these loop kernels onto the CGRA using our toolchain. So this work is actually we are presenting in ESV Codite workshop. So if you are interested, you can join that as well. So we have so this is a kind of the emulation setup on before fabricating the CGRA like SOCs, we are doing emulation on FPGA. So this is the emulation setup that we have in US, which is used to do the verification of the design. And so this is, so as Tilini also previously mentioned, we also have this tool chain called Revamp, which kind of focused on generating heterogeneous CGRAs from the homogeneous CGRA. So in homogeneous CGRA, all the PEs are similar, but based on based on the application suite that we can give as an input, the Revamp toolchain can find a heterogeneous version of the CGRA, which has a better, like a lower area as well as lower power, while still providing a similar or near the same performance as the homogeneous version. So this tool is also available open source, and you can see, so we have applied this tool chain in order to get a heterogeneous versions of existing homogeneous CGRs like address, HighCube, and SoftBrain. So the tool chain was able to infer the more power efficient and area efficient versions while keeping the performance same. So as a future works, we are currently developing this MLIR based end-to-end compiler. So as you know, the most of the deep learning applications are written in high-level languages like PyTorch and TensorFlow. So currently our Morpho toolchain basically takes inputs as a C codes, as I mentioned, but going beyond, we want to plug them the Morpho toolchain in a way that the higher level, the applications that is written in higher level can be easily offloaded to CGRA. So we are using MLIR based, we are developing MLIR based toolchain, integrating the Morpho toolchain as well. So if you are interested in this development process, you can also contribute and contact us. So yeah, that's the end of my presentation. So I will give the.
Thanks. Thanks. Yeah, so that brings us to the end of our presentation, and yeah, so we'll be happy to take any questions if you have. Okay, so if there are no questions, then thanks a lot, and we will be happy to answer any questions via email or any other methods. Thanks a lot. Thank you.
Thank you to Lika for the great session. It was really educational and helpful with the hands-on. So we will put up the video on YouTube as soon as we get, these Zoom files. And if you need the access to this file, just let me know. I will send the file to you.
Okay, sure. Yeah, that would be great. Thanks so much.
Okay. Thank you. Thank you so much.
Yeah, thanks.
Bye.
Bye-bye.